No card. Thank you. Bra, det var det.
Oh, I'm not.
Just or a little like. All of this.
Yeah.
Barney Ricketts, radio astronomer, that his real thing is interstellar simulation, understanding of. But he also has been doing radio pulsars and stuff. And Hans Parr works now
He gets some waves.
Brian Keating side of all
I should
that.
have brought like Kelvin or something. I'll just have him back here. Like,
Yeah.
go like this during the talk. Yeah, but you're not a stuffed moose, so it makes sense if
They're out.
It'll make no difference. Any resistance is too much.
They've got one telescope on.
My bug is that I get these fatal exceptions, or fatal errors, or whatever.
Sir. Good to
But
see you.
only when I try to compute transitions from J equals 4, J equals 2 states, other J equals 4, J equals 2 states, or J equals, no,
Hi, thanks for coming.
or
Yeah, we're just waiting for Hans.
the same thing for J equals 3.
He's
Well, it
there.
can also be preposterous too. Yes. It's
The door was locked, but you can try.
That's something, don't experiment. I'm trying to figure out, do we nail down specifically things that should be here?
Yeah.
And I identify it or reproduce it. Basically, I want to be able to solve it and say, very specifically, this thing is not anything else. Once I can do that, I can say,
Yes.
yes,
Yeah, we've been for
We have met, but we haven't really said we're.
yes, you should definitely be curious.
So Bill's out of town now,
And he's in
Australia or
Sydney,
somewhere.
For about 3 months.
So he'll miss most of the soccer season.
it's a star.
Yeah.
Or,
Well,
it looks like it's a star. That's
I'm a
good.
bit limited. So I'm now
Honestly,
back
yeah,
on
these are having some cool equations.
Hold on, how are you?
Pretty impressive.
Oh, yeah. The game's gone, that's the idea.
Stars which irregularly increase in brightness by a large factor, then drop back down to a quiescent state, initially called nova.
No, no, they're like, they're very rare.
Now I reprogram.
Or say, yeah, this is irregular.
All right, well, we can get started. We're here today for Eve Armstrong's thesis defense. Eve received her BA from Columbia University in astrophysics in 2002. She passed her qual here in 2005, and then had a minor diversion of medical leave that lasted 5 years. But everything's fine and wonderful now, and so she got back to working on her degree. She returned here in 2011 and has been working on it since. And while she was starting as a senior undergraduate, she started working with Joe doing observations of CVs, and she just continued doing that. And so most of her work has been while visiting Columbia University, but she is a UCSD grad student. She is also an adjunct professor at Cooper Union for the Advancement of Science and Art, and at the City University of New York. I believe she has a great interest in teaching science to not necessarily science majors. She has 2 first author papers in monthly notices and one more in preparation. Those are basically her thesis results. In addition, she's a co-author on about 8 more papers that came out over the years where her observations were part of the basis for the interpretations in those papers. And finally, she has a distinction that not many of us have. She has a publication in the Journal of Reproducible Results on non-detection of the tooth fairy at optical wavelengths. So CVs are not necessarily something that is a topic of study here in CAS, but I've learned a great deal about CVs by working with Eve, and the mind-boggling part of it for me is these binary systems are small enough that they would fit within the sun. So with no more ado on my part, go get them.
Okay. Yeah, I do. Thank you all for coming. Oh, thank you for the lights, Ken. So, I have studied the long-term evolution of the helium-rich cataclysmic variable stars using a method called time series photometry. And before I get into the studies that comprise my thesis, I'd like to explain to you what that means. So, a CV is an accreting binary system in which the primary component, the higher mass component, the mass stealer, is a white dwarf star. Here it is over here. Here's the lay of the land. And for now, I'm going to define a white dwarf as a star that has finished its core nuclear burning and is comprised mainly of helium and carbon in a degenerate state that is supported by electron degeneracy pressure. They're about the size of the Earth. And there's a secondary star over here whose makeup I will get into in a few minutes, and it is donating its matter, which is going into the spiral accretion disk around the white dwarf. And the hot spot right here is the area of enhanced luminosity where that stream impacts the disk. So these systems are experiencing continuous stable mass transfer over at least 10 to the 8 years. And the transfer process is not smooth, and it results in a variable brightening of this system on the order of anywhere between 2 and 20 magnitudes on timescales of minutes to tens of years. And the mass transfer process suggests that there is some sort of angular momentum drain on these systems. The disk dominates the light that we see. So when you look at the spectrum of these objects, you're seeing the disk material, which presumably came off the secondary, and so it helps you infer the nature of the secondary star. And the nature of the secondary star and the geometry of the system set by Roche geometry and the angular momentum loss guide the long-term evolution of these systems. And to remind you of Roche geometry, you have lines of equal gravitational potential in the plane. And the figure 8 here is the path of least resistance, the Roche lobe of the system. And the mass is being transferred from the secondary to the inner Lagrangian point L1 under the primary star. So I'm going to distinguish now between two different classes of these objects. The first are the hydrogen-rich systems. We know of about 2,500 of them. We look at them in optical light, and they peak in the V band, effective wavelength around 5,500 angstroms. Their orbital periods, and what I mean by that is the period with which the two stars orbit their common center of mass, is somewhere between 1 and 6 hours. And when you look at their spectrum, you see essentially strong lines of hydrogen and very little else. So we infer that the secondary in these systems is essentially a sun, a low-mass main sequence star undergoing core hydrogen fusion. The long-term evolution of these systems is governed by angular momentum drain, and we expect that in time these systems are shrinking. They're evolving to shorter orbital periods, they're spinning up in time. And that prediction is consistent with observations of hundreds of these systems. So the picture of the hydrogen CVs is pretty well fleshed out relative to their helium cousins. So we know of about 26 of these, and about 4 or 5 of those 26 should be considered candidates. So relatively few. They're systematically bluer. They also appear to be smaller in size. Their orbital periods are all shorter than about an hour. That indicates a more compact geometry and a more compact secondary star. And when you look at the spectra, you see essentially no hydrogen. And instead you see strong helium lines and products of helium burning. So the tentative picture we have is that this secondary has evolved to some extent beyond the main sequence and is somewhere on the spectrum between sun and fully degenerate white dwarf itself. Now, as for the long-term evolution of the helium CVs, angular momentum loss should shrink the binary. But a degenerate star has this property that as it loses mass, the degeneracy pressure lifts and the star will expand. So this secondary, if it's appreciably degenerate, will expand upon mass loss, and that will tend to lengthen the binary. So at some point, you expect there to be a kind of a tug-of-war contest between the angular momentum deranged shrinking the binary and the tendency of the secondary to expand upon mass loss, lengthening the binary. Who wins the tug-of-war contest? The prediction is that the secondary's degeneracy wins, and that these things should be evolving towards a longer orbital period. There's very little observational evidence for or against any particular model. So to summarize what I've said so far, we've got the big hydrogen guys, and this is approximately to scale. I did my best in Photoshop. So this is a sun, and this is a star evolving beyond the main sequence to a fully degenerate state itself. So the picture for the large systems is relatively well understood compared to that for these systems. And one question in particular is, what is the nature of this secondary star? What happens to a star after it leaves the main sequence? Applications of the study of CVs to broader areas in astrophysics. CVs are excellent labs in which to study the process of accretion. How you get a disk from a ring of matter to begin with, the physics of the matter in a disk. Rates of type 1a supernova, where they come from, various routes to formation. I probably will not discuss those today unless I get a question on them. Specifically for the helium CVs, what happens after you leave the main sequence? And in particular, the likelihood of a double common envelope phase. Long, long ago, before you had a binary, you had two main sequence stars in wide orbit. One of them, the one that's destined to become the primary white dwarf, becomes a red giant first, and that red giant atmosphere encapsulates the binary, call that the common envelope. And it seems that for the helium CVs, you had to let that happen twice. It had to go through two common envelope phases, and that seems to be a pretty unlikely feat of nature. And then finally, applications to GR and gravitational wave radiation. So the studies that I will talk about today aim to answer the question, what is the direction of period change, orbital period change in the helium CVs? And what does that imply about the nature of the secondary star in these systems? And I'm going to attack this question through two routes. The first route is studying the distribution of CVs as a group. What we want to do is chart the distribution of orbital periods in time. If we can look at the system and identify a proxy for time, then we can do that. And I'll explain to you how. And the second study is doing a direct timing of the rate of orbital period change in one particular system. That's what I'd like to focus on today. If we have time at the end, I will also mention some other studies I've done on signals that appear to be related to a picture of tilted accretion disks in CVs, which is a problematic picture for CVs. So if I have time, I'll get there. And if I don't, anyone who's read my dissertation, if you have questions on chapter 5 or 6, I'm happy to answer them. Okay, so I've said a few times that we have angular momentum drain occurring in these systems. Why do I say that? So this purple equation is the angular momentum of a binary and Kepler's law. And A is the orbital separation between the centers of mass of the two stars. Now, if you assume conservative mass transfer, that is, all of the matter transferred from the secondary is ultimately accreted onto the white dwarf. Nothing's lost. Then you get this relationship between the rate of angular momentum change, J dot, the rate of mass loss from the secondary star, M2 dot, which by definition is negative, M2 is losing mass. Q, the mass ratio, which is the ratio of the secondary to the primary mass. And A dot, the rate of orbital period change. Now, if you set J dot equal to 0, if there's no angular momentum loss in the system, then A dot is greater than 0. That is, as the mass transfer goes on, the separation increases. At some point soon, the secondary will detach from its Roche lobe, about 100 years or so, and continuous mass transfer will stop, and we will cease to see these objects. That is not observed to happen. Continuous mass transfer appears to be going on for at least 10 to the 8 years. So to save our picture here, we suggest that, okay, J dot is less than 0. There's some sort of drain on the system. What could it be? Again, I'm going to focus on these short period objects, the helium CDs. And for systems with orbital periods shorter than about 2 hours, angular momentum loss via gravitational wave radiation is likely to be the dominant cause. Where gravitational wave radiation is the propagation of curvature through space-time, in this case due to the orbit of 2 dense masses in a binary system. So here's the tug-of-war that I was referring to earlier, where...
Sorry to interrupt
Yes,
this.
please.
This gravitational wave radiation is calculable if you know them, if you assume something about the masses. Is it numerically working out that that J dot comes out to be about the right value?
Yes, and I will get there.
Okay.
Yes, it does. I think you're referring to this general equation.
Oh, okay.
And, yes. I would like to talk about that within the context of one particular study. I think if I give you a direct example, it'll make more sense in that context. Okay. So the first term on the right is J dot over J, and if we attribute that to gravitational wave radiation, you've got that equation on the left. Then the term on the right describes the secondary's response to the mass loss, where the mass radius relation of the secondary, which essentially characterizes its degree of degeneracy, is contained within the m dot term. So you see that for a while, if GWR is winning out, and if the secondary is not appreciably degenerate, then both of those terms on the right are going to tend to shorten the orbit. But as degeneracy increases, the tug-of-war begins, and at some point the second term should win out. So the general picture here is that these systems are evolving down toward a shorter orbital period governed by gravitational wave radiation, at which point you reach a period minimum somewhere. And then after that, the dominant force is the expansion of the secondary upon mass loss, and you're evolving towards a longer orbital period from then on. And one evolutionary calculation has come up with a period minimum around 10 minutes. More importantly, for our purposes today, we can directly measure the rate of orbital period change in a system with a period around 10 to the 3 seconds, using a baseline of photometry of about 10 years. Okay, great. So the first study aims to answer the question, what is the sign of P dot? Or what is the secondary in these systems? And the first way we're going to go about tackling that is by looking at the distribution of helium CDs that experience an outburst. And I'll explain to you why. The first thing I want to do is explain to you how we do this. So these are our toys at the MDM, the Michigan Dartmouth MIT Observatory on Kitt Peak, Arizona. We have a 1.3 meter and a 2.4 meter telescope there. And we get about 2 to 3 months of time per year on these telescopes. And more importantly, we have the Center for Backyard Astrophysics, which is a worldwide network of both professional and amateur observers who coordinate their schedules to get long baselines of photometry on single objects. And when I say long, I mean decades. And this is important for 2 reasons. First, if you want to study the long-term evolution of these periods, you need that long baseline to do it. And secondly, observing from different longitudes on Earth and staggering the time of observation within a 24-hour window will significantly suppress the phenomenon of aliasing you get in the power spectrum of the objects. And you're going to see examples of aliasing in every power spectrum that I showed you today. So this is photometry. You get a finding chart, use the Downs and Shara catalog, and this is a 5x5 arc-minute field of view, where the binary is the one dot in the crosshairs. It's not resolvable by eye on the image. There's a near neighbor separated by a few arc seconds, but that's just some other star. Then you point your telescope there, and it can be quite difficult to acquire your field of view if the dots are changing size on you, which happens when they go into outbursts. And this was the 2001 super outburst of WZ Sagitti, where you see it over here, it's at a magnitude of about 15.5. And here it rose to a magnitude of 8. And just to point out, this star here is now this one. So you take a series of these images, you take thousands, hundreds of thousands of them, and that creates a light curve. Oh, let me specify. You take a light curve of differential photometry with respect to a comparison star on the same field whose magnitude is known to be stable, to 1 part in 10 to the 5. So you subtract the light curve of your comparison star off the light curve of the CV, so you know that any variability that's left in the CV light curve is intrinsic to the CV and not due to some cloud that's passing by. Here are some light curves. I'm showing you this just as an example of the vast variation in behavior that you see in these objects. They do not all do the same thing. This one second from the top is an eclipser, and most of the other variations you see here are due to some sort of outburst behavior.
So all these people in the worldwide collaboration use the same comparison star. They have all agreed. Is that right?
Ideally. But sometimes, someone's telescope's got hot pixels in some area. Sometimes it doesn't work out. And in that case, what you want to do to calibrate among different people's light curves is you want to make sure there's at least some overlap, and you want to mesh them. But if you use the same comparison star, which is ideally what you do, you get a difference in magnitude among observers of just plus or minus 0.05. So that's how we compare. Yeah.
Can you go back to that one?
Yes, yeah.
Can you point at aliasing? I'm not really sure what you're talking
Oh, sorry. These are light curves. I'm talking about power spectrum.
Oh, okay.
When you take the power spectrum of the light curves, then you'll see what I'm talking about.
Oh, okay.
Okay, so for this study, we're particularly interested in systems that experience outburst. And here's what I mean by outburst. The rate at which the secondary donates its mass to the disk is greater than the rate at which that mass can then be transported through the disk onto the white dwarf. So you get a buildup of matter in the disk. The disk gets hot, opacity increases. At some point you reach a critical viscosity when a large amount of matter is dumped onto the white dwarf. And the dissipated gravitational potential energy loss in the well of the primary causes that brightness outburst that you see. In addition, sometimes, shortly after the rise of a system to maximum light after outburst, this is the light curve of the photometry I showed you a few minutes ago. This is WZ Sagitti having risen to a magnitude of 8, and now it's fading away. I apologize for this stuff in the middle. Please ignore it. These are echo outbursts. They have nothing to do with anything I'm going to talk about today. Shortly after rise to maximum light, around day 10 or so after outburst, these, what we call super hump modulations, appear in the light curve. They dominate all other modulations. And they're called positive super humps because of the way they look, and because their period is slightly longer than the orbital period. The interpretation of this is as follows. So large disks are tidally unstable to the gravitational pull of the secondary star, and they can go elliptical. And if that happens, they can start to recess in a prograde direction with respect to the orbit. And the disk material that's no longer on circular paths will collide and the dissipated energy is this modulation that you see. And the superhump period, PSH+, corresponds to a beat between the orbital and precession motions. Now that's very useful for us, because what our aim here is, we want a proxy for time in these systems, because we want to chart as a distribution their orbital periods in time. Q, the mass ratio, goes as time. The secondary is losing mass to the primary as time goes on. Q is very difficult to measure for non-eclipsers, and very few of our systems eclipse. One of our systems eclipses. But let's stick with the mass of the secondary for a minute. Now, say you have an elliptical disk, so you see superhumps in this system. As the secondary loses mass, its gravitational pull on this elliptical disk will decrease. The precession rate will slow, and the corresponding beat period, superhump period, will speed up. So if we define, sorry, got ahead of my slides. If we define epsilon to be the difference between superhump and orbital period all over the orbital period, epsilon should serve as a proxy for Q, and hence as a proxy for time. And from eclipsing hydrogen CVs, empirically we found that epsilon is about 0.2 Q. And epsilon is directly measurable for systems that experience super outbursts. So that's why we're looking for these. Now this has been done extensively for the hydrogen systems. So here you see this is a log-log plot of epsilon versus orbital period. And to remind you, epsilon goes down with time, so time's pointing down in that direction. And the picture, oh, I should explain the lines. The black line is essentially a secondary that's a sun. These dots are systematically below it because if you put an isolated sun into a binary system, it'll be distended due to the mass transfer process. So the binaries, the secondaries and binaries are systematically larger for a given mass than isolated stars. And this dotted line extends into the range in which degeneracy becomes important. But what I want you to carry away from this plot is that the picture for hydrogen CVs is evolution towards shorter orbital period. That's what this distribution is telling you. So now for the helium CVs. Oh. Now for the helium CVs. I want to talk to you about one specific system that I studied. This is CP Eridani, and it's got a 70-year history of outburst and quiescence behavior. So we know this thing goes into outburst. We also knew prior to our observations that it had some sort of periodicity of about 29 minutes of unknown origin. I'm giving this to you also in cycles per day, frequency units, because all of the power spectra that I showed you are going to be in cycles per day. So we obtained a 9-day baseline in quiescence on this object and a 2-day baseline during outburst. And this all comes from the 1.3 meter telescope at MDN. Okay, so up on the top left is a representative 5 or so hour window of the light curve. The whole 9 days look like that. At the bottom left is the power spectrum of the full 9 days. We represent a light curve as a sum of sine waves of increasing frequency. So we're mapping from the time domain into the frequency domain. That's what the power spectrum is. And on the x-axis here, this is in cycles per day, frequency in cycles per day. And essentially on the y-axis, what you have is the power at a given frequency. So this is the ALA structure I was talking about. You see a main peak here at 50.34 cycles a day, but it's surrounded by this picket fence sort of pattern, and that's called aliasing. And it's a result of the sampling rate with which you sample your signal. Here's a little cartoon. Say your samples are the black dots. Unbeknownst to you, the signal is the black sinusoid. Well, you don't know that. All you can do is fit your dots. So you fit them with the black sinusoid and the blue one and the green one. And all of them will show up in your power spectrum. The blue and the green are aliases. So it can be very difficult to identify the real signal. And that's what I meant when I said that observing using different observers to observe it, to stagger their times within a 24-hour window can suppress that pattern. Okay, so the question here is, what's what? We want to identify the orbital signal and we want to identify the signals. So the first thing we do is we look at the strongest feature in the power spectrum, which is obviously this thing, one peak at 50.34 cycles a day. And there's something else over here. I'll talk about that in a moment. Is there something else in here? In addition to the alias structure, there seems to be something hidden underneath that main signal. I've blown it up for you here. Is there anything in that structure that's independent of the main signal's alias structure? To answer that question, what you do is you model that 50.34 cycle a day signal as a sine wave of a particular amplitude, phase, and frequency. And you sample it using the sampling rate of your original data. And you take the power spectrum of that. And that is the spectral window up in the top right. And you compare this to this, and anything that that's in here that doesn't show up in here is independent of your main signal. And so it does appear that there's some strong, well, there's something that shows up very weakly over here, but not nearly as strongly as it does over here. And again, there seems to be something buried underneath the main signal. So you subtract off your model from the light curve. That's your residuals light curve. And you take the power spectrum of that. It's your pre-Whiteley power spectrum, and that's this. And now, you see that what remains is a 50.78 cycle a day signal. And 101.57 is the first harmonic of 50.78. Now, orbital signals tend to be highly non-sinusoidal in waveform, so they tend to produce harmonics in the power spectrum. So the first guess here is that this is the orbit, and this is possibly a superhump. This is quiescence, but this system goes into outbursts frequently, and in such systems, sometimes the superhump doesn't completely die away during quiescence. All right, so now I'm going to keep the quiescence data on the left. I'm going to keep the light curve and the power spectrum. And on the right, I'm going to bring up the 2-day super outburst data. So now you see this, we'll call it a sawtooth modulation, which is characteristic of superhumps that dominates the light curve. And when you take the power spectrum, you see a 50.30 or so cycle a day signal. The frequency resolution isn't nearly as good here because the baseline is much shorter. And when you subtract off the 50.30 cycle a day signal, there's nothing left behind. Now I want to be clear, this power spectrum does not have the frequency resolution necessary to identify two signals in this structure. But from other observations of this object, longer observations of this object in outburst, we know that during outburst there's just one signal there. And in outburst, the superhump tends to overwhelm the orbital period to the extent that you can't see it at all. One final clue comes from the waveforms. You fold your light curve over the period of interest and look at the shape. Look at the bottom first. The bottom is the the outburst data folded on the 50.30 cycle a day. The period that corresponds to 50.30 cycles a day. And you see this sawtooth modulation. Up here in the middle, this is the quiescence light curve folded on the 50.78 cycle a day period. Sorry, I'm confusing frequency and period. Let me bring up the actual numbers here. Oh, and in the middle you see that that's not sinusoidal. It looks actually more like a W shape, which is characteristic of orbital signals. So our identifications here are that the orbital signal is the weaker 50.78 cycle a day signal, and superhump was the dominant one. Sorry, up at the top. The top you have the superhump that's faded a bit during quiescence. It's a quiescence light curve folded over the superhump. Okay, so we just classified things so far. Now we're going to, I want to explain to you the means by which we get these measurements. So now we do this with all the systems we can find that experience superhumps, that experience outburst. And again,
a separate curve on the bottom of the three pictures. There seems to be a separate pattern. You see that? a band that is separate from the rest of them?
No, in this one, the one down bottom?
Yeah, a little lower, yeah. If you point to, you see that sine wave
I
line?
think that's the linear decline.
Is that one observer that disagrees with the rest of them, or?
I think that's the linear decline that you see in the previous slide as the outburst fades.
I don't understand.
There's a band that's
So
separate
it's
from the
getting
big band.
fatter. So there's
Yeah.
Oh, do you mean,
Yeah.
you mean
No.
this,
Little
the
lower
two
with your,
peaks?
little lower with
Look
your.
at the bottom
The
set
lower
of
parts.
points in your plot.
Yeah.
This is that separated from your main band, which is more dense.
Down here?
Yes.
Those
Yeah.
points versus the ones above them, he thinks says something
Maybe
else.
one observer being. It doesn't bring it back.
You know, I don't see that, the points are denser up towards the top than they are down here. They get more and more just diffuse as you go downwards. So I don't really see a significant change in the
Eve,
pattern.
Eve, if you corrected for the, if you go back one slide, 2 slides, 3 slides, there we go. No, no. So have you corrected for that decline in the outburst
The
brightness?
the trend here?
Yeah.
No.
Okay, so I
No.
think that's probably, there's a few low cycles.
Okay.
Some astronomers do trend, some do not. I don't like, I like to minimize the manipulations I do to the light curve before I take the power spectrum.
Very good.
Okay, so to remind you, this is our plan here. We're going to identify superhuman orbital periods in order to use this relation to chart evolutionary history. All right, so this is the an initial plot. All right, let me back up. This is the Hindenburg balloon plot in epsilon P orb space, where these over here on the right are the hydrogen guys again. If you have questions about these models, we can talk about it later. I'm going to focus on the helium guys. There are 7 dots in here that are in the shaded region. And this extremely tentative picture suggests that the helium CVs are evolving towards a longer period. That is, their secondaries are well represented by, well described by degenerate or partially degenerate objects. So I've updated that plot. Here's the update. I've added 3 points and corrected 1. Used a refined empirical relation for epsilon of q, and put them in the context of 2 model curves. The bottom curve represents a fully degenerate helium-carbon white dwarf secondary. And the top curve represents a partially degenerate star that is still burning helium at the birth of the system. And I should define birth of the system, at the onset of Roche lobe overflow and continuous mass transfer begins. This plot suggests that these objects are evolving towards a longer period in time. The red dots come from our superhunt measurements. The 2 green on the right come from a different measurement of Q, come from spectroscopy. I should comment on these gigantic error bars here on the 5th from the left. That comes from an uncertainty in the superhunt period. I tried to illustrate a few minutes ago that this can be a very tedious process. And that particular system displays several signals, and we haven't yet firmly identified the identities of all of them. So I've allowed for a range there. That's all I wanted to say. Yes?
Just for clarity, if you have a non-degenerate star, what would the band of that just look like genetically?
If you have a non-degenerate star, then you're back in the realm of the hydrogen CVs, and actually, this is why I had this up for comparison. You have systematically higher masses of the secondaries in those systems, and they obey the opposite relation as time goes on. Okay, so to summarize this first study, the key finding is that a snapshot of 10 helium CVs indicates that these systems are evolving towards longer orbital period, and that they have secondaries that are well described by partially degenerate objects. Yes,
One more question. What does the band actually represent?
Oh, I'm sorry. The band represents a a range of masses for the primary star. The primary is 0.6 to 1.2 solar masses, and the solid lines represent the average. A typical mass is 0.75 solar masses. Sorry,
So
Lanja.
0.6 would be the upper and 1.2 is the lower of the upper light blue band. The solid blue.
No, I understand the question. I'm trying to work it out.
Sort of looks like that.
Yes, yes. Okay, same question.
Are we coming back to that slide?
We're coming back, yes, we
Oh.
are. Yes, in the grand finale, we're coming back to it.
Too good to, just stab things, just
I'm,
leave so fast.
you're right, you're right. No, I'm happy to talk more about it. But I want to put it in context with the second study before I do that. So the second study, we're asking the same question. What's the direction of evolution of these systems? This time, we're going to do it by looking at one object and timing its orbital period. The object is AM Canvan, which is the best studied helium-CV. It was the first discovered. And helium-CVs are actually also called AM Canvan stars. And it's essentially a permanent state of outburst, meaning it's always showing superhumps, and it's very bright, magnitude about 14. It's got an orbital period around 1028 seconds, and we obtained an 18-year baseline of photometry. Not just me, many people. It's
She started out.
difficult to do that from the womb. It's tedious business anyway. Okay, and here's how we do it. It's a method called pulse timing. We use the observed minus calculated diagram to illustrate it. What you do is you define a model sinusoid of a constant period. It's called your test period, and you assume that that does not change. And so you extrapolate its phase into the future. And each arrival time of maximum light, or minimum light, your choice, is a calculated value of the phase in time. It's your C value. Then you take your light curve, and you chop it up into subsets, and you fold each subset enough times to obtain a sufficiently well-defined waveform to do the same timing with your data. And each of those timings is an observed value, an O value. So as time goes on, if there is a difference between that test period and what your signal's actually doing, that is, if your signal's lengthening or shortening in period, you should get an accumulated difference between those two values. Specifically, here's the O minus C diagram, where you've got time on the x-axis and that phase difference on the y-axis. And if there's no difference between the test period and the actual period, then you get a straight line. P dot equals 0. If your orbital period is shortening, P dot is less than 0, you get a concave down parabola. And if it's greater than 0, you get a concave up parabola. To put our observations in context, before I show you our results, this has been done for 2 helium CVs. The first one is ES-SETI, it's got a period around 10 minutes. And from a 9-year baseline, here's the O minus C diagram. Now I want to point out a few things. First, the scattering points is not convincingly above or below the x-axis. So these authors concluded essentially that there's no evidence for orbital period change in any direction. Upper limit of P dot is 1 part in 10 to the 11th. And these parabolas here are various fits, assuming different mass radius relations for the secondary star. The shallowest parabolas are the most fully degenerate objects. And this big, large curvature parabola is a helium star, which is essentially still undergoing core helium burning.
So even
Yes.
in doing this process, you assume a sinusoid for the C.
Yes.
But the knowledge of that value must change this picture. So how do you decide on the
Okay.
the
Yeah.
value to use?
Yeah. So if you're, I think I know what you're asking, but I try to draw it. If your test period is, say, 1028.00 seconds, never mind, I can just say it in ones. But your actual period is constant and slightly shorter, then you're gonna get a linear, it's gonna be a line, a straight line of negative slope.
So have you fitted then for that, you've made the slope 0?
Yeah, yes.
So you make a test period and then you adjust your test period until the slope is 0? Is that right?
Yeah, that's right.
Can I ask a question about this?
Yes.
Now, if you, there are all those curving lines there that make you kind of dizzy there. If I might be rendered so dizzy that this question is just not meaningful, but if I imagine them gone, and I just look at the points relative to the flat line, I would imagine that there might be some very weak, not significant, but a weak positive curvature that is holding water trend. It just looks like the points at the right are systematically a little bit above, and points at the left are not systematically a little below. So while this conclusion up here, absolute value less than 1.5 times 10 to the minus 11 is probably that's the correct conclusion. Probably the actual fit was a little bit on the best fit is probably a little bit on the positive p-dot side. Is that right?
I see what you mean.
You're one of these authors, so I thought you would.
Yeah, I see what you mean. You're
No, you
saying
haven't
that, you're saying that the better linear fit would be,
Oh, no, not linear, no, again, this is, like I say, I'm not claiming it's significant because it doesn't look like it's good enough to be significant. But if you just did it blindly and you weren't worried about annoying referees, referees or something, I would guess from looking at it that the p-dot would be, slightly positive with an error bar large enough to encompass both. It looks like there's a little bit of curvature.
Yeah, you just want that sort of darker line that's real close to the
Yeah.
straight line, sort of is
Yeah, that
doing what you're saying.
Yeah, that little darker one, looks like it's probably a little bit there.
you mean this one?
Yeah.
Yeah, so in his paper, that parabola is consistent with a double white dwarf system. So he concluded that this could be
Oh.
a double white dwarf system.
But it excluded some of the other scenarios.
Yes. Well, he excluded this one. He excluded the helium star channel. I will explain what I mean by channels in a few minutes, but he did rule out certain
So each one of these curves, both the ones that are consistent and the ones that are not consistent, represents a specific set of physics assumptions?
Each parabola represents a different mass radius relation for the secondary,
Oh,
and that would imply a makeup of the secondary.
so that's why they're there.
Maybe one thing that helps is do we know what the uncertainties on the OMIC value data points are? They're just points.
When we get to our result, I will be able to illustrate that. And I think that might, I can come back to this for comparison, and I think it might give you a better idea if I show you our data before I answer that question.
Can you discuss sort of the distribution of the points? It seems like for a given x-axis value, you might have two y values. So I'm not sure how to read this.
Okay,
I don't know
well-
why there's a cluster of points near x equals 5 Kelvin cycles versus. Can you
Okay,
explain that? to
so
me?
I'll take this as an example. These two x values look as though they're occurring at the same time. They're not. They're probably separated by a few days.
Okay,
So
each of
there
those
is a
things-
difference there is a separation in time among all of these points, between all of the pairs. But some of them look like they overlap because they were taken so close together. Whereas this gap here could be, oh, well, this is 9 years, so this gap is probably, a year or so. So,
Okay, so it's sort of how much data you have for a given, it's like an observation. And so there's a lot of time between two observations and it's hard to get. It's
Right.
hard to